Hi, everyone. Welcome. We're going to get started in just a couple of minutes. Hi, everyone, and welcome to the Headwall webinar for non-contact prediction of blueberry bricks using hyperspectral imaging. Just a few FAQs. And before we get started, my name is Marissa DuPont. I am the marketing specialist here. This webinar is being recorded and should be available for viewing within 48 hours. We will answer as many of your questions live as possible, and additional questions will be answered by email after the conclusion. You can email those to marketing@headwallphotonics.com. Our agenda, we're going to start with a brief introduction and then an introduction to Headwall. What is hyperspectral imaging? The blueberry brick study, recorded demonstration, Q&A, and then we'll wrap up with some exciting news. You can ask questions using the questions panel on your GoToWebinar controls or on your phone. Now I'd like to introduce our panelists, William Rock, PhD, Product Manager of Machine Vision at Headwall in Bolton, and George Killian, Application Scientist, Headwall in Bolton, Mass. as well. All right, take it away.
Thank you very much, Marissa. And before I get into the official introduction of Headwall Photonics, I just want to highlight that this webinar will be about two blueberry brick studies that we did. One in the MV.C NIR and one in the NIR. The MV.C NIR one, we were able to separate good and bad berries. In the NIR one, we were able to predict the bricks or the sweetness of blueberries. So if you stay tuned through the whole webinar, we will take you end to end in the process of both creating and deploying those models and talk about how well that they worked as well. And so Headwall Photonics is who we are, and we are the ones that, again, made this blueberry webinar. We are a company that was founded in 2003, and we were recently acquired by Arsenal Capital Partners. We have 3 sites across Massachusetts and are headquartered in Bolton, Massachusetts, and we also have another site in the Netherlands as well. Currently, Headwall employs approximately 100 highly skilled employees and has about 40,000 square feet of engineering and manufacturing facilities across all our locations. Headwall concentrates on servicing 3 core markets and has a global reseller and distribution network. And so if you're interested in products from any of those markets, please contact Headwall. So the 3 main market areas that Headwall addresses are machine vision, remote sensing, and OEM optical components and assemblies. So today's webinar will concentrate on the machine vision sector of the business, where we will be highlighting the products used to collect data in a benchtop setting that can then be deployed for online and real-time measurements. But just to make a note, Headwall also supplies hyperspectral imagers as airborne packages for remote sensing, and also provides OEM optical components and assemblies, including diffraction gratings, spectrometers, and spectrographs that can be integrated right into the customer's products. So as far as the machine vision products go, the two machine vision products that were used in today's study are the MV.C NIR and the MV.C NIR. So the MV.C NIR is a NIR hyperspectral imager that covers the 400 to 1,000 nanometer wavelength range. It is also the most compact imaging spectrometer in its class. As you can see by the scale shown by the hand holding it, it's about the size of a deck of cards. So it's a very compact and light imaging spectrometer. The MV.C NIR is a product that will be released soon. It is our machine vision NIR product covering the spectral range of 900 to 1700 nanometers. So this gives you a little bit more chemical information than the NIR product, which is centered more around the visible range of the spectrum. And the NIR, MV.C NIR will have gigabit Ethernet connectivity, and it comes with a variety of different locations to mount it to address any of your mounting needs for deployment. And finally, the last product on this page is the MV.X. The MV.X is a NIR hyperspectral imager that comes with onboard processing and ingress protection. So this product can be deployed directly above a process line in challenging environments because it has that ingress protection, and can directly provide actionable information because onboard processing comes with it along with the imaging spectrometer. So all in one box, you have image acquisition, image processing, and the output of actionable information. And all of today's studies were done using the new perClass MIRA stage. So this is another new product in Headwall's machine vision line of products. So the perClass MIRA stage is compatible with any of Headwall's machine vision hyperspectral imagers. So that includes the MV.C NIR, the MV.C NIR, the MV.X, and the Headwall's micro hyperspec SWIR 640. So if you're interested in a benchtop deployment of any of those sensors, this would be a great solution for you. The perClass MIRA stage fits into a single ruggedized Pelican case that can be shipped as kind of standard checked luggage in an airport. So it's compared to other stage systems, it's a very compact and easy to transport design. It can also be taken out of the case, unpacked, and set up in a matter of minutes, and it is designed for use with the perClass MIRA software, which gives you an integrated platform for acquisition, training, and deployment, as you will see demonstrated later in this webinar. So there are many different applications of hyperspectral imaging across a variety of different marketplaces. In today's webinar, we'll be focusing on blueberries, which of course fits into the food category. There are many other common applications of hyperspectral imaging for food, including measuring the Brix or predicting the Brix of many other different kinds of fruits. You can see in the image below is a previous example that we had done where we predicted the Brix on oranges. Hyperspectral imaging is also a powerful technique for foreign object detection, as has been previously deployed with almonds, as can be shown in the middle image. And it can also be used to detect adulterants in things like herbs and spices, as shown in that top image up there. Other non-food market areas include recycling, so sorting of different plastic materials and other recyclables, the pharmaceutical industry, so it could use hyperspectral imaging for things like defect detection, color consistency, and coating consistency, and also looking for cracks and chips on the coating. And finally, the agriculture is another strong area where hyperspectral imaging can be deployed. And in agriculture, possible applications are single seed analysis, plant phenotyping, and early disease detection. So please contact Headwall if your area of interest is any of those, or even another area that wasn't listed here. Hyperspectral imaging really can be deployed in a very wide variety of applications. So now I'd like to give a brief introduction of what is hyperspectral imaging, so we can try to understand how it does the magic that we're going to show later in the webinar. So from a most simplistic sense, hyperspectral imaging is the combination of imaging and spectroscopy. So it can really leverage the power of imaging and the ability to separate things spatially, and the power of spectroscopy, which allows you to use spectral signatures to identify different materials. And there are several different ways that one can conceptualize a hyperspectral image. So the one depicted on the far right here is that of hundreds of grayscale bands, where each band represents a different color or wavelength in the data cube. And so we can think of that as a stack of hundreds of grayscale images, where an RGB image is, say, a stack of 3 grayscale images, one representing the red channel, green channel, and blue channel. Instead, in hyperspectral imaging, we have hundreds of channels. As someone that comes from a spectroscopy background, I prefer to think of hyperspectral imaging as an image where there's a full and continuous spectrum at every spatial pixel in the image. And that is really highlighted on the next slide, where here is an image that I love to show to highlight the power of there being a spectrum at every spatial pixel. So this is an image of 6 common white powders. In your classic camera phone image, all those powders pretty much just look like white powders. Hard to differentiate them by eye or by an image. But each of those different white powders has a very distinct spectral signature in the near and SWIR spectral range that can be seen to the sides of each of these images. So if you have a full spectrum at every spatial pixel, you can create a model that looks for these different spectral signatures and assigns a class to every spatial pixel in the image based on its spectral signature. So the image on the far right is an example of that, where every spatial pixel in the image has been assigned a class based on which of these white powder spectral signatures it most closely identifies with. And then we color coded those classes in the image for easy visual consumption. So how does a hyperspectral imager work? How do we get a spectrum at every spatial pixel that we can use for the identification of materials? So the image that you see here on the left is a cutaway of a Headwall microhyperspectral imaging spectrometer. And so it includes several components, the first of which is that 4-optic lens that you see on the far right side at the bottom. That will gather all the light and project an image onto the slit. And what the slit will do is block away all of the image except for just a sliver of the scene. And then the light passes through to a spectrograph that consists of 2 concave mirrors and 1 convex diffraction grating. And what that will do is re-image that slit and disperse the light. So it will make the blue light go to one side of the focal plane and the red light go to the other side. And all of the colors in between are at pixels all in between there. And it will project that slit image and spread out all the different colors in that slit image on the focal plane and produce an image like the cartoon we have on the right, where every column in that image I like to think of as a spectrum. So I like to think of a hyperspectral imager as over 1,000 spectrometers crammed into one box. So every time a line is gathered or an image frame is gathered, we are gathering over 1,000 spectra in our MV.C NIR imaging spectrometer. And each of those 1,000 spectra can be analyzed and assigned a class. And so because a hyperspectral imager is a line scanner, it will, you need to have motion in order to gather an image. And as you just saw pass by on the screen, that was a depiction of an image passing by the sensor and the line light. And as that image passes by, we will gather one line of the scene at a time. And as we stack all those lines together, we build up a whole image. And perClass MIRA can analyze each of those lines as they are coming through to also produce real-time classified results. And so that's what the image waterfall in the middle is highlighting, just kind of a classic RGB image of a line scanner. And on the far right, it was depicting processing each line of data as the image is passing under the sensor. And now that you know how a general hyperspectral push broom scanner works, we're going to go over the components of Headwall's new complete hyperspectral imaging package, including the perClass MIRA Stage, which we have highlighted up there right now. This package also includes the lights that come with the stage as well. And in this particular case, we're showing the MV.C NIR. As I mentioned before, the perClass MIRA Stage is also compatible with the MV.C NIR, the MVX, and the Micro Hyperspec SWIR 640. Here's the lens that's used to gather the image and project into the image spectrometer, the computer where we store our acquisition and analysis software. And finally here, of course, the sample that you need to put down on the stage. And the stage is traveling in the direction depicted by the arrow, can travel either way back and forth on that linear stage. So now that we've been introduced to Headwall and hyperspectral imaging in general, let's get into the meat of the webinar, the Blueberry studies that were done. So why did we choose to do a couple of studies on blueberries? First of all, it's a high value fruit. So the price per blueberry compared to other products, it can be pretty high. And also accurate grading is required to separate the fruit into fruit consumption grade versus processing juicing grade. And that grade assignment can greatly affect the value of the blueberries. So it's important to be able to accurately separate the blueberries into high quality consumption grade versus processing grade as accurately as possible, so you can continue to capture all the value from your good blueberries and maintain a good reputation in the marketplace for supplying high value fruit. Blueberries are commonly inspected by hand, which is inherently a very subjective way to classify anything, and a time-consuming and expensive way. And also the standard ways to get the sweetness or the Brix value requires destroying or juicing the fruit. And so hyperspectral imaging can be used to address many of these shortcomings in the current way we process blueberries, as we show on the next slide. So hyperspectral imaging can be used to rapidly scan high volumes of product, and can be used to eliminate the manual sampling that's used to separate the good from the bad fruit, as we will show in our first VNIR study. You can obtain real-time actionable results, and as far as the Brix studies go, you can also scan high volumes of product and obtain the Brix values without the need to destroy the fruit. So the two studies that we did both used two varieties of blueberries, the Jersey and Darrow varieties, and all data was acquired using the perClass MIRA software and the perClass MIRA Stage. So the first study that I will talk about is the study that used the MV.C NIR, which was used to separate blueberries into high and low quality blueberries, and these blueberries were categorized by expert growers. So we went to the grower and we said, which ones are the high quality ones that you put on your shelf in the supermarket that people buy and eat, and which are the ones you rejected from that you would want an automatic sorting for. And the second study that we will highlight is the Blueberry Brix study, where we used Headwell's MV.C NIR, and we also got Brix measurements using a handheld digital refractometer. So how was the Blueberry V-NIR classification done? So again, as I introduced before, we had an expert separate the blueberries into good and bad. And then we took them back to our lab, and we took an image of all good blueberries, and we took an image of all bad blueberries. And then we used perClass MIRA to train a classification model, in this case containing 3 classes, one for the background, which is a standard class that we always have, one for good blueberries, and one for bad blueberries. In the case here, we assigned the color yellow for a bad blueberry and the color green for a good blueberry. So as can be seen here, in this particular feasibility study, every single bad blueberry, save one, was correctly predicted by the classification algorithm to be a bad blueberry. So we consider that a very high success rate. And on the next slide, we'll show both the results from the good blueberries and the bad blueberries. And so you can see in both cases, all the good blueberries are recognized as good except for one, and all the bad blueberries are recognized as bad except for one. So again, maybe that's an indication that we're showing you real results here. We're not trying to fudge anything. These were the models that we created from these actual blueberries. And so unfortunately, we got one wrong. But this still indicates that this is a very robust algorithm that gets it right about 90% of the time in this case. So the next study that we would like to talk about is the Blueberry Brix regression study. So the plot that you see on the right includes measurements of many different blueberries. So this includes both Jersey and Darrow blueberries, both at the beginning and at the end of the growing season. So this is one complete model that was created across the entire growing season of 2 different varieties. So we really kind of tried to stress ourselves here in showing that we can predict the Brix value of blueberries across an entire season and in multiple varieties using a single model. And the blue markers on the graph are the training data, while the green markers on this particular graph are the test data, so it was data that were not included in the model. perClass MIRA tools were used to perform cross-validation, where we shifted what is the training and what is the test set among all the blueberries that we measured. This cross-validation showed an average RPD, or residual prediction deviation, of greater than 2 for this model. And so if you're not familiar, RPD is a common metric to assess the quality of a regression model, and values over 2 are considered to be quite good. The perClass MIRA software, again, was used to predict these blueberries at a high rate. Cross-validation was used to confirm the quality of the model, and we repeated the measurements at the beginning and end of the season. And later on, when we show our video, we will show you details of how the blueberries were acquired, how the Brix measurements were taken, and how a regression model was built end to end using perClass MIRA. But before we get to that demonstration video, I just want to again summarize and highlight the model development and deployment process in hyperspectral imaging. So for both of these models, we followed a very similar experimental procedure, where step 1 is, of course, acquiring the data. And step 2 is analyzing that data. We have on this initial graphic downloading the data, but with the new updates to the perClass MIRA Stage package, if you get the stage and the MV.C NIR or MV.C NIR, you will be able to acquire data directly to the computer that also does the analysis, so you won't need to download the data to a separate computer. You'll have that data on the computer, you'll be able to create a classification model, and you'll also be able to immediately deploy that classification model and watch the results in real time while making the perClass MIRA stage go back and forth. So this gives you instant feedback and enables rapid corrective action when deployed either as a test stand or over a conveyor belt. It eliminates the risk of doing subsampling, which is a very common method these days. When if you need to destroy a blueberry to see how sweet it is, you can't destroy your whole product line. You have to destroy a sub portion of that. And so this would allow you to sample an entire product stream if deployed over a conveyor belt. And you can transfer your model between multiple different sensors. Well, the sensors of the same type. So you could have an MV.C NIR that you use for acquisition and another one that you use for deployment. In summary, perClass MIRA software, in conjunction with the perClass MIRA stage, can be used to acquire and create a strong blueberry classification model using the MV.C NIR that allows you to separate good from bad blueberries, and a very strong regression model to predict the Brix of blueberries using the MV.C NIR. This would allow producers to better grade blueberries and better assign value to the product based on its quality, and would give a non-destructive way in order to do all of this assessment. So wouldn't require them to destroy any of the product to attain this information. And if you are a blueberry producer or have any other application where you think hyperspectral imaging could be deployed to help your products grade their value, or approach any of the other applications that we mentioned throughout this webinar, please do not hesitate to contact Headwall. We would be excited to work with you to assess the feasibility of your application and work on deploying it down the line. And so now, with no further ado, we would like to show you more or less how the sausage was made, how we went from data acquisition to model training to deployment of a blueberry Brix model. Please excuse us as we have some slight technical difficulties here. We will show you this demonstration momentarily. So sorry for the delay, everybody. As we sort out the technical difficulties with the video, we'd like to move on with the question and answer part of the presentation, and we will get the video to you momentarily. But in the meantime, please ask us your questions and we'll be excited to answer them.
I got the video. Okay. We just can switch to the video.
I've been told that we have the video available now, so we'll switch back to doing Q&A at the end. Please enjoy the video.
They give you back.
Okay, first question is, what wavelengths were used to train the Brix regression model?
I can answer that one. So when making a regression model in perClass MIRA, you're able to quickly and easily be able to select or deselect any sort of wavelengths that you might use within the whole range. So while the NIR goes from 900 to 1700, in this particular model, we went from about 930 nanometers to about 1400 nanometers. And that seemed to be the range to which perClass MIRA was able to create the most effective model for predicting the Brix and blueberries.
Okay, the next question is, do you know what parameters were used to determine good versus bad berries by the growers?
Yeah, so the growers had indicated that they were looking for a few different things. Of course, bruising, visible bruising is the easiest thing, but also the firmness of the berry that they would be able to tell from. And then if there was, since we had a particularly rainy season here in New England this past summer, if there was any sort of water damage or mold that was on the berries that they were looking for as well.
Okay, you mentioned the cross-validation tool. How does that work exactly?
Yeah, so the cross-validation tool is within the perClass MIRA software. Every single image has a name, but some of those images might be duplicates of the same berry sample. So in perClass MIRA, you can write a regular expression to note which images are associated with which samples, and then you can run through different iterations of regression modeling where a certain percentage of those samples are used for training, and then the remainder are used for test. And then you can run through those multiple different iterations, recreating the regression model each time, being able to make sure that your model works over the entire range of samples as opposed to either all training or a curated sampling being used for training and test.
Okay, when using the refractometer, you press the berries into the well. Do the pulp and seeds affect the data?
I'll take that one, and we're sorry that you didn't get to see us press the blueberry into the refractometer yet. That was in the video, but no, that did not affect the data. So I guess the easy answer is we tested this empirically as well with low pulp and high pulp juices. But really this makes some sense because the refractometer is really just looking at the refraction of light at the surface layer between the optical element there, which is covered in a very thin layer of water. So it's really not looking at any of the stuff that's floating on the top. And so we found that that did not affect our Brix measurements really at all.
Did you try building a Brix model in VNIR as well? What was its performance?
Yeah, we did build both the classification model in both the VNIR and the NIR and a regression model in the VNIR and the NIR. And the reason why this is the case is that in some fruit applications that we've done in the past, the VNIR has been the model to which, the range in which the model works best for regression and predicting. And while the VNIR had a relatively strong regression model, if memory serves me correctly, with an R-squared value of around 0.8, the NIR model worked that much better. In the video example that we weren't able to see, when we had built a model with just a single variety of blueberries with only a small sampling of berries, the regression model was around, the R-squared value for the training set was around 0.99. So it really comes down to every application is unique. And so it's important that when we're starting to build a model, we check all the different possible wavelengths with all the different sensors that Headwall has available to make sure that we're making the best model we possibly can.
Can this be used with tomatoes?
Yeah.
Actually, yes, our colleagues at perClass have done a fair amount of work with tomatoes. So I am not intimately familiar with that acquisition project, except that I know that they did it and they had some high success there. So if you're interested in a tomato application, please contact Headwall. We can put you in contact with perClass as well, and they would be the experts to go over how this works with tomatoes.
How long does it take to create a regression model?
It takes longer to juice and determine the Brix values for the 25 or so samples of berries than it does to build a regression model. The workflow that you would go through is if you're looking to do a single berry analysis regression model, you would first collect the data, you would crop to have images of each individual berry, and then you would import the regression values, and then right then and there you're able to kind of build the regression model within perClass MIRA and do those different iterations of training and test that I mentioned earlier with the cross-validation. All in all, that process takes about 5 to 10 minutes, not really, depending, of course, there's so many different applications. Some studies or some applications require lots more samples than just 50 or so blueberries, while other applications are able to work really quickly with only a few samples.
Do you think this system could be applied to blueberries on the plant in greenhouses or fields? And if so, what challenges would you expect?
From my understanding, especially in the New England region, when it comes to growing blueberries outside, there's a lot of netting and canopy that's applied over the blueberries. And as Will mentioned earlier, our sensors can be applied in remote sensing applications as well. So this would be a particular hurdle when it comes to looking at blueberries from a remote sensing side of hyperspectral imaging. When it comes to greenhouses, we've seen projects where our sensors are deployed on gantry systems, which would certainly prove much more effective and give the opportunity to be able to get much closer to the sample itself and produce higher spatial resolution images for potentially better results. But if that is an application you're interested in, of course, please feel free to reach out and contact us. That is really the next step, right? Being able to take it from the lab to outside to the fields and the growing.
Is there any drill core scanner with your cameras?
We do not have an off-the-shelf drill core scanner with our cameras, but if you have an application that requires drill core scanning, please contact Headwall and we'll be happy to work with you to find a custom solution.
Okay, we'd just like to mention that due to the technical difficulties, we will send out a link where you can view the presentation that the video that we're going to show. Okay, and then, yeah.
Yeah, and thank you very much, Marissa. And so to wrap up this webinar, I would just like to highlight that Headwall really likes to emphasize that you get the best value with our products if you buy them bundled. So if you buy a full solution that includes the perClass MIRA stage and software and a Headwall hyperspectral imager, and a computer. So all the pieces you need to set up and start measuring hyperspectral images and generating models and deploying those models same day, very quickly. So the best way to get the most bang for your buck and to have the highest success rate as a user of our instruments, we really strongly recommend purchasing these full packages. We're also running specials on these through March 31st. And so to get more details on those, please contact your local sales rep. And another thing that I would like to highlight that I'm very excited about is the upcoming release of perClass MIRA 5.0. So this new software release has many very exciting new features, including a more efficient acquisition workflow that includes data compression, the ability to have simultaneous dual camera scanning all in the perClass MIRA stage, and the ability to have an operator mode, which is a simplified interface that can be used to deploy solutions. And that's just a couple of the new features. We are running a webinar series in the next month or two in several different regions to highlight the new features in this upcoming release. And we'd be very excited for you to attend that upcoming webinar series as well.
All right, thank you so much for attending today. We'd like to give special thanks to Will Rogg and George Killian, as well as Mikhail Jabran and Ross Nakatsuji, who did our technical work. Thank you very much. Have a great day.